Hello, good morning SH2 students. Welcome back to physics lesson. Today we will still discuss about radioactivity actually. This chapter is for A level, but it is related to the chapter that we just studied before, the radioactivity. The chapter of nuclear physics, chapter 31, you can see it from your textbook page 489. You can open also your textbook while listening to me here. You can also have a cup of coffee or tea while listening to me. And I do hope you have opened the EPOS also, yeah, for the announcement of new school year. So I am waiting to see you soon in SH3 later. And I have a big surprise for you in SH3. Okay, now back to our lesson. Again, I'm telling you that this chapter, nuclear physics, is so much related to the chapter that we have discussed before, the radioactivity. In radioactivity chapter, we have studied about how to balance the nuclear equations. I always tell you that the right side of the reaction and the left side of the reaction needs to be equal. We also have studied about these things. You see the green box here. In alpha decay, the nucleon numbers decrease by 4 and the proton number decrease by 2. Because why? Alpha decay is the decaying of helium nucleus. In beta minus decay, the nucleon number is unchanged and the proton number is increased by 1. Why? Because beta minus decay is the decaying of an electron. In beta plus decay, the nucleon number is unchanged and the proton number is decreased by 1. Yes, because it is positron decay. In gamma emission, there is no change in nucleon or proton number because the gamma emission is the emissions of energy only. Yeah, I also have give you some questions related to this kind of things. I give you the graph, and then after that I give you one elements, and then I'm asking you whether it is having beta decay or alpha decay. Okay, and then you need to make the graph. These kind of questions also we have discussed. And of course, I believe that you can answer also the questions in page 490, which you need to answer later. Okay, now the important new things here is about the mass and energy. You guys, of course, very familiar with Einstein, Albert Einstein. Albert Einstein is the father of modern physics. Yeah, I ever tell you that what is the difference about what is the difference of modern physics and also the mechanical physics, the common physics that carried by Galileo, by Newton, by Archimedes. The law that they made in mechanical physics, the law that Galileo made, the law that Archimedes made, the law that Newton's made, is not applicable in a very small thing, in a very small particle, in subatomic particle. Yeah, it is not applicable. So Einstein, made a new law for subatomic particle. Actually, the law from the law from Einstein is not only applicable in subatomic particle, but it is also applicable in big particles. But since the number is too small, then some people, just ignore it. we still can use the law from Newton's and also the law from Archimedes and Galileo to solve problems in mechanical physics, common mechanical physics, but not in modern physics. Now, in modern physics, we need new rules, we need new laws. One of it is about the mass and energy law. Mentioned here in chapter 16, we saw that energy is released when the nucleus of an unstable atoms decays. How can we calculate the amount of energy released by radioactive decay? Now, we will start by considering a stable nucleus, this nucleus of carbons. This consists of 6 protons and also 6 neutrons, so it is very stable. Fortunately for us, because we have a lot of this form of carbon in our bodies, this is very stable nuclide. Actually, there are other forms of carbons, nuclides also, but the one that is very stable is carbon-12. This means that the nucleons are bound tightly together by the strong nuclear force. It takes a lot of energy to pull them apart. We have also discussed about this, that in the nucleons, there is strong nuclear force that pull them together in the nucleons. One interesting thing is this one. Okay. The first thing that you should know is that the total mass of a stable nucleus is always less than the total mass of individual protons and neutrons put together. Now, but before that, I want to introduce to you about this one first. It's important to know that the mass of different nuclei, since nuclear interactions are all about mass energy conversion. And to calculate the mass in subatomic particles, we use ununified atomic mass unit, which is U. U is 1.6605 times 10 to the power of negative 27 kilogram. These also have been studied before. So we do not use the unit of kilograms for subatomic particles, but we use the unit of U, ununified atomic mass unit. Okay, while we're calculating the numbers of protons and neutrons and also the mass of protons and neutrons, of course we will need to use this amount. We need to use this ununified atomic mass unit. The total mass of a stable nucleus is always less than the total mass of the individual protons and neutrons put together. So it is like this one. Okay? So if it is been together, while it is separated, the mass is slightly different. You see here, this is for the nucleons of carbon-12 when it is been together. And then this is the mass of 6 neutron and 6 proton, which has been scattered. We see on the right hand side are 6 protons and 6 neutrons, the result of dismantling the nucleus. When we dismantling this nucleus, of course it will become 6 neutron and 6 proton. The surprising thing is that the balance is tipped to the right. The separate nucleons have more mass than the nucleus itself. This means that the law of conservation of mass appears to have been broken here. Have we violated what was thought to be a fundamental law of nature? Of course, at first we think that the nucleons of carbon, which is not been dismantling, is equal to the mass of 6 neutron and 6 proton, but it is not. So where does this additional mass comes from? Okay, comes from the binding, what we call as binding energy. Okay, binding energy per nucleon. So this binding energy, we can see it here. This binding energy depends on the types of the nucleons. As you can see here, the binding energy of helium nucleus is around 7. And then after that, it will increase, yeah, based on the increasing number of protons and neutrons in the nucleons. So more protons, more neutrons in the nucleus needs more binding energy. This binding energy, when the nucleons separated, will become the mass. That is why the balance here will go to the right. Why? Because here there is mass of 6 proton and 6 neutron plus the binding energy here, okay? And for this part, the binding energy has become mass. At this part, the binding energy is still in the form of energy. At this part, the binding energy has become mass. That is why this part is heavier than the other part. To calculate, we can use the Einstein mass energy equation. This is very famous. E equal to mc square. E is the energy, m is the mass, and c is the speed of light. Previously, I'm telling you that the modern physics actually can be applied also to mechanical physics that we have studied before, yeah, in the beginning of SH2. You see here, when bodies are in higher energy state, they have more mass than in a lower energy state. A bucket of water at the top of a hill will have more mass than when it is at the bottom, because energy has been transferred to it in carrying it up the hill. This happening. And one more example, a tennis ball traveling at 50 meters per second will have more mass than the same tennis ball when it is stationary. In everyday life, the amount of extra mass is so small that it cannot be measured, but the large changes in energy which occur in nuclear physics and high energy physics makes the changes in mass significant. For example, in real life, okay, we have a tennis ball which the mass is 150 gram, and then the speed of this tennis ball, let's say 50 meters per second. Now, we calculate first the kinetic energy by this moving ball, okay, using half mv squared. Then we will get 187.5 joule. If we put this energy into the mass energy equations, so we will get mass equal to the energy over the speed of light squared. The energy is 187.5, and then the c of light is 3 times 10 to the power of 8. This one needs to be squared. Okay, and then we get 2.1 times 10 to the power of negative 15 kilogram, which is very small. That is why in mechanical physics we do not use this law, because the amount of the changes between the mass and energy is very small. But if we consider it two very small particle, then this change from mass into energy, from energy into mass, is significant. Okay, it is significant, then we need to calculate it. Next, we can use the mass values to calculate the mass that is released as energy when nucleons combine to form a nucleus. Another example, this one for the mass of carbon-12. Yeah, carbon-12 consists of 6 protons and also 6 neutrons. The mass before, you just need to times it and plus, and then after that the mass after, this one's usually given. Then we can calculate the mass difference before and after the nucleons dismantled apart. When 6 proton and 6 neutron combine to form the nucleus of carbon-12, there is a very small loss of mass known as mass defect. The mass defect of a nucleus is equal to the difference between the total mass of the individual separate nucleons and the mass of the nucleus, which we can calculate using this formula. Now you can see also the work example in page 493. This one for an oxygen atoms, yeah, before and after it is dismantled. And we can calculate the energy supplied to dismantle the nucleus. So guys, for today, I'm asking you to make an answer. Yeah, you don't have to write down the questions here because